Hey everybody, so welcome to the very first video in a series of videos that's going to be talking about the reactions and mechanisms in all the different chapters of this class. So obviously we're in chapter 6 right now, so we're going to be starting with chapter 6. And I'd like to do videos like this for a lot of the reactions in all of the different chapters of this class. So like I said, we're starting with chapter 6 in this video. So the very first reaction that we learn in chapter 6 is SN2. Okay. So we're going to be talking about SN2, and there's going to be a video after this that's going to talk about SN1. And I think I'm going to talk about hydride shifts, methyl shifts, and ring expansions all in their each in their own videos, basically. I think that'll be the best way to go about that. So anyway, let's get right to it. So we're going to talk about SN2 here. So there's four key things that we kind of need to remember whenever we're thinking about SN2 reactions. So SN2 reactions prefer methyl halides. And remember, X just stands for fluorine, chlorine, bromine, iodine, any halide, right? It doesn't matter what it is. They prefer methyl halides over 1 degree, and they prefer 1 degree over 2 degree, and 3 degree is really, really bad. Okay, so if I have a methyl halide, it's going to go through the reaction much more quickly than if I have a 1 degree halide. All right. So that's one thing to remember with SN2. Another thing to remember with SN2 is the solvent that we use, right? So for SN2, what we use is the polar aprotic solvents. So there's a lot of different polar aprotic solvents, DCM, DMSO, HMPA. There's a full list in the slides of polar aprotic solvents, so I would definitely look at that. I think that would be to your advantage to know all the polar aprotic solvents by heart, basically. I think that's going to help you in the long run. So polar aprotic solvent, this just helps the reaction go forward. Another thing is that we need strong nucleophiles, right? So we need a strong nucleophile. And what does that mean? Well, for our cases, that usually means that it has a negative charge, right? So if you see a negative charge in a nucleophile, very, very good chance that that's a strong nucleophile. Okay, so that's kind of what we're talking about there. And then the very last thing with SN2 is that there's a inversion of stereochemistry. So what does that mean? Well, we'll see kind of what that means here in a second. I think that it would be to our advantage to do a couple of examples here. So I'm going to do two examples that kind of bounce off of each other. So the very first example we're going to be doing is with 2-bromobutane, okay, and this is actually 2R, or R2-bromobutane, right? And what we're going to do is put this through NaOH and DCM, okay? So on the bottom of the arrow, I write my solvent. On the top of the arrow, I write my nucleophile, right? So if I look at NaOH, how do I know this is a strong nucleophile? Well, NaOH, is there a charge on NaOH? No, right? So I said negative charge means a strong nucleophile. So how do I know this is negatively charged? Well, sodium always has a +1 charge, right? So if sodium always has a +1 charge, then what is the charge on this OH? Well, the charge on the OH, in order to balance out, has to be -1, right? So OH has a minus charge. Remember that sodium isn't really doing anything in the reaction, okay? So sodium's not the nucleophile. Don't write sodium as the nucleophile. Please don't do that, okay? Our actual nucleophile is OH minus, okay? All right, so then the product. So inversion stereochemistry, right? So that just basically means if I start on a wedge, then my product is going to be on a dash every time, okay? So I flip the bond, and then I take the halogen and replace it with my nucleophile. So I'm just going to write OH where Br was. I'm done. That's it, okay? It's that quick. It's that easy, okay? Take the halogen, replace it with a nucleophile, flip the bond. I'm done, okay? And just to kind of hammer home that inversion, I started with R, and I end, if you do the R and S configuration for that, this one is S. Okay, so I go from R to S. The same thing is also the case if I start with S instead. So this one is S, 2-bromobutane. I'm going to put it through the exact same reaction conditions. So then all I'm going to do is flip the bond, write OH where the bromine was, and I'm done. And if we look at this product, this is R. So I go from S to R or R to S. Okay, so that's my inversion of stereochemistry. All right. So this is how we do the reaction. Like I said, very simple. Now what we can look at is the mechanism. Okay, so the mechanism, again, just a one-step reaction. So this is a very quick mechanism as well, not a whole lot going on here. In the mechanism, we like to draw out all the electrons and all the byproducts. We can show exactly what's going on in the mechanism. It makes everything kind of a little bit more clear. So what I'm going to do is do the mechanism for this very first one here, this 2-bromobutane, R2-bromobutane. So we have bromine here, and bromine has these 3 electron pairs on it, right? And what's going to happen is our nucleophile is going to come in and it's going to donate an electron pair to the carbon that's bonded to the halogen. Why? Because the carbon-halogen bond, or specifically the carbon-bromine bond in this case, is polar, right? So if it's polar, then bromine has a higher electronegativity than carbon, right? So that tells me that carbon is going to have a lower electron density around it, and bromine is going to take that electron density and have a higher electron density around it. So that means that bromine is going to be slightly negatively charged. It's not actually going to have a charge, but there's going to be a slight negative charge around it because it's going to be hoarding the electrons. And then on the other hand, carbon is going to have less electrons around it, so it's going to be slightly positive. So these negatively charged electrons on this nucleophile are actually going to be attracted to that slight positive charge in that carbon. So that's why it's going to attack. So the other thing to mention here is that the bromine is large, right? Pretty big atom, and that's going to cause the nucleophile to want to come in from the opposite side the bromine's on, right? So the bromine is on a wedge, right? So the bromine's coming out of the page or the board or towards you, however you want to think about it. And since it's coming out, right, the hydroxide is going to attack from the opposite side. So that's why the hydroxide ends up on a dash, right? So it's going to come from the back. It's going to be a backside attack, right? So I'm kind of drawing it like from the back, if that kind of makes sense and how that's being drawn there. And then all I need to do after I draw this, I need to say at the same time that this is attacking, this bond is going to be breaking, right? This is a one-step reaction, so all this is happening at the same time. So the hydroxide attacks, but at the same time, the bond breaks, okay? So the bond breaks at the same time that that's being attacked, and then what do I get? Well, I get OH here on a dash, and then I used 1 electron pair to make a bond, so I just have 3 electron pairs left, and then my byproduct that I don't typically draw the byproduct, but in the mechanism I want to draw the byproduct to show it. Like over here, I would never draw like plus BR minus, like there's just no point. But here in the mechanism, it's important to draw that. So that's why I've drawn it here. So then I just draw plus my BR minus, and that's it. Okay. So let's look at one more mechanism here really quickly just to kind of hammer this home. Let's do a primary. So this is a primary iodide, right? So it's going to go through the reaction very quickly. And let's say that our halogen, or our nucleophile, sorry, is NH2 minus. So what's going to happen here is that this is going to come from the backside, and iodine is going to leave at the very same time. And then what do I get? Well, all I do is just write NH2 to replace the I. And then what's my byproduct? Well, my byproduct is the I minus with that extra pair of electrons. And that's it. So this is everything that we kind of need to know for SN2, and this is what we need to know as far as the mechanism goes. Very short mechanism, like I said, one step. Next video, we'll be talking a little bit about SN1, and that one's a slightly more involved mechanism. So hopefully this was helpful. I appreciate you watching, and I will see you next time.